Emotion recognition in conversation has advanced rapidly, but most modern architectures share a fundamental blind spot. They treat global context as a monolithic signal, feeding every utterance, speaker history, and topical reference into a single attention or pooling mechanism. The problem is that context is heterogeneous. Topics, events, speaker dynamics, and actual affective cues get mixed together, and not all of them equally help predict emotion. What we actually need is a way to isolate the stable, dialogue-level emotional undercurrent and use it as a reusable prior. This is exactly what AtmosERC tackles. The authors introduce a concept called dialogue-level affective atmosphere. Think of it as the latent emotional baseline that persists across a conversation, distinct from transient utterance-level spikes or shifting topics. Empirically, you can see this in the data. Dominant emotions cluster far above uniform baselines across standard benchmarks, and valence trajectories form locally coherent segments. Conversations have a persistent affective tendency, and AtmosERC builds a framework to explicitly estimate, extract, and deploy that tendency. The core of the method is a relation-aware graph extractor. Instead of flattening a conversation into a sequence or treating it as a bag of utterances, AtmosERC models each dialogue as a heterogeneous graph. The node set contains two disjoint subsets: utterance nodes, initialized with frozen RoBERTa embeddings, and speaker nodes, initialized with learnable identity embeddings. Edges are not arbitrary. They are carefully constructed around four distinct relation types that capture different affective dependencies. First, interspeaker dependency connects utterances from different speakers within a sliding window, modeling short-range crosstalk influence. Second, intraspeaker dependency links consecutive turns by the same speaker, preserving speaker-specific emotional continuity. Third, global semantic similarity creates sparse long-range edges between utterances that exceed a cosine similarity threshold, allowing the model to catch thematic or emotional echoes far down the dialogue. Fourth, utterance-speaker affiliation connects each utterance directly to its corresponding speaker node, enabling speaker-aware aggregation. Once the graph is built, the model applies relation-specific graph filtering. This is where the architecture gets clever. Instead of mixing all edges into a single message-passing step, the model stacks multiple layers where each layer propagates messages independently per relation type. For a target node, it aggregates neighbors under each relation using a relation-specific GAT, then fuses the outputs with element-wise max aggregation. This acts as a low-pass filter over the graph signals. Transient, utterance-level noise gets smoothed out, while stable affective patterns are preserved. After nonlinear activation and layer normalization, the model stacks these operations across layers to progressively refine node representations. To extract the actual atmosphere prior, the framework concatenates the layer-wise representations for each node, projects them through a learnable linear layer, and applies max pooling over the utterance nodes. The result is a compact, fixed-dimensional vector that represents the dialogue-level affective atmosphere. Crucially, the speaker-conditioned representations are retained separately, providing auxiliary priors that capture individual speaker affective tendencies. This extracted prior is designed to be reusable across different ERC paradigms. The first application is a lightweight, atmosphere-aware sequential decoder. The atmosphere vector initializes both the forward and backward hidden states of a BiGRU, meaning local utterance dynamics are decoded under a global affective baseline. Simultaneously, the speaker-conditioned priors initialize speaker-specific GRU states that only update when that speaker actually produces an utterance. At prediction time, the model fuses the atmosphere-conditioned utterance state with the active speaker state, passes it through a linear classifier, and outputs the emotion label. This proves that explicit atmosphere modeling isn't just for massive architectures. It directly boosts lightweight sequence models. The second application targets the growing class of LLM-based ERC methods. LLMs struggle with long-context reasoning and often lack task-specific inductive biases for effective trends. Since they cannot consume continuous vectors, AtmosERC introduces a verbalization head. This is a lightweight feed-forward layer trained to map the atmosphere vector to the dominant emotion label of the training dialogue. During inference, the head predicts a discrete emotion label purely from the input context. This label is then injected into the LLM prompt as a fixed instruction. The overall effective atmosphere of this dialogue is no backbone fine-tuning, no prompt restructuring, just a plug-in prior that gives the LLM explicit global effective guidance before it even sees the target utterance. The results validate the approach across four major benchmarks: IEMOCAP, MELD, Emory NLP, and DailyDialog. On lightweight ERC, AtmosERC outperforms strong sequence, transformer, graph, and knowledge-enhanced baselines. The gains are particularly pronounced over graph-based methods like Dialog GCN and DAG-ERC, confirming that the advantage comes from converting structural context into an explicit effective prior, not just from graph aggregation. DailyDialog shows a smaller margin, which the authors attribute to its high proportion of neutral utterances diluting the atmosphere signal. For LLM-based ERC, the plugin variant consistently improves general-purpose models like GPT, Gemini, and DeepSeek, with gains up to 3 percentage points. It also boosts ERC-specific architectures like InstructERC and CausalERC. The authors run a diagnostic analysis, replacing the predicted atmosphere with a ground truth dominant emotion proxy, which yields even larger gains. This confirms two things. The prompt injection mechanism is highly effective, and the verbalization head still has room to improve in accurately capturing the latent atmosphere. Beyond raw accuracy, AtmosERC demonstrates robustness. The authors test prediction recovery after local emotional deviations. When a model encounters an utterance that breaks the dialogue's effective trend, it should ideally return to the dominant emotion on the next turn. AtmosERC leads in next utterance and pair-level recovery across most datasets, showing that the atmosphere prior acts as a stabilizing anchor. Ablation studies further confirm that removing any of the 4 relation types degrades performance, and dropping the speaker-conditioned prior consistently hurts results. The heterogeneous graph structure and explicit atmosphere extraction are both necessary. This work makes a clear contribution to conversational AI. By formally defining and extracting dialogue-level effective atmosphere as a reusable prior, AtmosERC separates stable effective tendencies from generic contextual noise. It works for lightweight sequential decoders. It plugs directly into LLM prompting without architectural changes, and it improves robustness under local emotional shifts. The main limitation remains the latent nature of the atmosphere itself, which currently relies on dominant emotion proxies for supervision. Future work will likely explore richer multimodal signals and more precise effective supervision to tighten the gap between estimated and true atmosphere. If you're working on emotion recognition, context modeling, or LLM prompting strategies, this paper offers a clean, technically sound blueprint for explicit effective prior extraction. The code and datasets will be open-sourced, so it's worth diving into the implementation if you want to experiment with relation-aware graph filtering or atmosphere-guided decoding in your own pipelines.